So Richard, you are ready, right?
Yeah, I'm ready. I can.
Okay. So hello everyone and welcome to today's edition of our extremal and probabilistic webinar. Before we start with our today's speaker, let me quickly go through the practical things. So they have been the same since the beginning, but still this talk is being recorded and will be posted on YouTube within 2 days or so. So please bear that in mind if you are asking questions, it will be recorded. If you do have any question, then please either unmute yourself and pose it directly, or if you have a problem with your audio, then write it in the chat and I will remind the speaker or notify the speaker. And the talk will be for roughly an hour. There will be time for questions in this official part, and then I will stop the recording, and you can either ask any further questions, or we can have a chat on any related topic, sort of a bit looser. Okay. So now it's my pleasure to introduce Richard Montgomery from Birmingham. And Richard will talk about some new results with Hong Liu concerning cycles of various lengths in graphs. So Richard, please.
Thank you very much. Thank you all for coming along, and thank you for the organizers for the invitation. So as Jan says, I'm going to talk about cycle lengths in graphs mostly, and everything I talk about was joint work with Hong at the University of Warwick. Okay, so I want to think about the cycle lengths in graphs. So I don't really care about how many cycles and so on. All I care is about the possible cycle lengths. So let's define the cycle space of a graph, this C of G, such which is a set of integers L, such that I can find a cycle of length L in my graph G. And one thing I want to know is given the average degree D of G, can we say anything about the cycles that are in G? So maybe the first thing to note is that whatever you tell me the average degree of graph G is, I might not have any odd cycles. So we'll also think about the odd cycles in G. And in this case, if we want to force some odd cycles in G, a very natural thing to do is to think about the chromatic number. So given the chromatic number, chi of G, can we say anything about the odd cycles in G? Okay, well, maybe a first note about the cycle space based on the average degree is that it's quite easy to show that the cycle space number of possible cycle lengths must go to infinity with the average degree of a graph. But that statement is not necessarily so interesting. Those cycles may be very long. So in some sense, the cycle space would be very sparse. So in 1966, Erdős and Hajnal suggested this sum as a measure of the density of the cycles in a graph. If I take the harmonic sum of the cycle lengths in a graph, then when is that large? So they first asked in their paper, does this sum tend to infinity? Can we make it arbitrarily large as we make the chromatic number arbitrarily large? And perhaps but they also suggested maybe just the average degree should be sufficient to do that. So what kind of lower bound could we hope for? Well, if we look at the complete bipartite graphs, if we take this harmonic sum of cycle lengths, then we're missing all the odd cycles. We just have even cycles, so it's about the sum of the even numbers up to D. So it should be asymptotically a half log D. And this is kind of a very natural conjecture, but it's written down in 1975. They're just conjectured this is a lower bound for any graph with average degree D. The sum of the cycle space, this sum here, should be at least a half log D asymptotically. And we have some really good progress on this. In 1984, Jarvis, Komlosh, and Simaridi proved that this harmonic sum is at least some constant times the logarithm of the average degree. Okay, so this tells us something about the density of the cycle space in a graph, G. So it's well known that if I give you the average degree, you can't tell me that a graph contains a cycle of a specific length, and the same if you tell me that of the chromatic number. So in either of the situations, due to in the odd cycle case, that's very true. So even if the chromatic number is very large, we're not going to get these odd cycles. So can we say instead of just one cycle length, what if I give you a sequence of cycle lengths? Can you avoid every cycle length in those? So those are the two types of questions I'm going to consider. Some sort of density measure, we're going to use the harmonic sum from Erdős and Hajnal, or can I avoid all of the cycles lengths in a sequence? As I said, it's going to be a bit different whether the cycles are even and the cycles are odd. So 2 squared, that's going to give us 4 cases. So given the average degree, can I say something about how dense cycle space is, or can I find some cycle length in a sequence? And the same, we're going to study instead the odd cycles, how dense is it, and can we find some cycle length in a sequence? So I'm going to take that bottom kind of table and blow it up there, so we have just the same text. And I'll make these questions a little more concrete. So on the left-hand side, we're thinking about even cycles. So we have this result of Garifas combination summary. I said that the harmonic sum is at least some constant times the logarithm of the average degree. And we have this conjecture of Erdős, the constant implicit should be a half minus literal 1. And if we're looking for an even cycle in some sequence, then a nice example to use, and it's written in one of Erdős's papers in '84, by making the average degree of a graph arbitrarily large, can we force G to contain a cycle whose length is a power of 2? So those are the 2 main examples I'll take for even cycles. And then for odd cycles over here, to force the chromatic number to be large. So we have Erdős and Hajnal's odd cycle problem from 1981. So they asked simply, does this harmonic sum, but just taken over the odd cycle lengths, does it tend to infinity as the chromatic number tends to infinity? And we can also think about, can we find some specific length in some odd sequence? So why don't we think, by making the chromatic number arbitrarily large, or at least some constant, can we force the graph to have a cycle whose length is a prime number? Okay, so I'll cover a little bit more background on these even cycles. I already covered quite a bit of background in this density case here. So what about specific sequences? So we will say a sequence of even numbers, or in this case just a sequence, is unavoidable with high average degree if there is some d such that if the average degree is at least d, then one of those numbers is in the cycle space. And just reframing the question I had in the last slide then, are the powers of 2 unavoidable with high average degree? This seems to be kind of a surprisingly hard question. So the first sort of thing we know about unavoidable sequences is that Bolomash proved that if the sequence is an arithmetic progression which has even numbers in it, then it's unavoidable with high average degree. That was a conjecture of Burr and Erdős. And then much later, Verstraete in 2005 proved that an increasing sequence with density 0, which is unavoidable with high average degree, does exist. So this is a non-constructive argument, but it confirms a conjecture of Erdős. So we know that some such sequences must exist, but it is not known any explicit sequences. The closest we've got to finding explicit sequences that are unavoidable with high degree is a result of Sudkov and Verstraete from 2008. And what this does is that in lots of different sequences, it says they're unavoidable, except their methods don't work in graphs which are really, really sparse. So in particular, the class of sequences are ones that are exponentially bounded. So each term is bounded by at most a constant times the previous term. And this covers all the sequences like the parse of 2, obviously. And then it's unavoidable with high degree, except if the graph G has average degree, which is really sparse in terms of its number of vertices. So it's exponential, but exponential in the iterative logarithm of the number of vertices. So the first thing I'll talk about today about even cycles is some work that Hong and I began a long time ago, actually. So about 5 years ago, we started thinking about a problem of Thomason on subdivisions, which I won't go describe for time. But this was about 5 years ago, and we worked off and on it for a long time, and we realized it has some implications for cycle things. So what we're able to do is able to find a large interval. So given a graph G, we can find a large interval in which we can find a cycle with length every even number in that interval. So here's a theorem for you. So as long as the average degree of a graph G is D, which is at least some constant, then we can find some large R. So R is not much smaller than D, such that we have this interval of even integers in the cycle space from log to the e at bar up to R. So this is kind of what we're doing. We're constructing lots of different even cycles. So if we ask the implications to what I just talked about previously, if we have this theorem, so I know that the harmonic sum of the integers in the cycle space is at least the harmonic sum of integers in this interval here for some R, which is at least this sum. And then as R is large in terms of D, then it's also going to be at least 1/2 minus little of D1. So I'll recap in a few slides all the kind of implications of this. But when it comes to specific sequences, so that's the density of the cycle space. When it comes to specific sequences, sigma 1 up to sigma 2, sigma 3, and so on, if an even increasing sequence eventually appears in each possible interval, log 8 to the R, up to R, then it is unavoidable with high average degree. So you have these different intervals ranging over R. And I know that if by forcing the average degree high, I can find one of these intervals so that all their even numbers appear in the cycle space. So a sequence can only be avoidable with high average degree if it can avoid those intervals. So in particular, I'll talk a little bit about how tight this is, but an implication of this rather easily is that if an even increasing sequence is exponentially bounded, then it's unavoidable with high average degree. So that's what we have for even cycles. Then for odd cycles, we can similarly define a sequence is unavoidable with high chromatic number if by forcing the chromatic number to be at least some constant, then we can always find one of the entries in the sequence in the cycle space. Ooh, I'm missing an odd there. So it should obviously be one entry in the odds cycle space. And then my question before just becomes, are the primes unavoidable with high chromatic number? So in general, there's less known about the odd cycle lengths. So for example, we only have in 1992, Garfis proved that as the chromatic number of a graph gets large, then I skip this slide, then the odd cycle space, this is supposed to be, of a graph G also gets large. And as a result of Sidikoff and Verstraat from 2008, that says if a chromatic number is at least K, then I can find some interval of consecutive integers, odd or even integers, in the cycle space, which is the number of integers is linear in K, and they all belong in this cycle space of the graph. Which is a nice result. But if we look at the harmonic sum of this, it could still be very small. These consecutive integers could be huge compared to k. So they did look as well at the harmonic sum here, and they could prove again it's part of lots of results they have for cycle spaces or cycles and lengths and graphs. And again, it doesn't, they're great techniques, they don't quite work on if the graph is very sparse. In this case, they can prove that this sum tends to infinity if the independent ratio of a graph tends to infinity. So that's a relaxation of the chromatic number, and it shouldn't be going to infinity extremely slowly compared to G. So I'll try to explain later how you can get from even cycles to odd cycles in our constructions. But we prove a very similar theorem for odd cycles. So for h epsilon greater than 0, there is some k naught, such that if the chromatic number is k, is at least k naught, then I can find an interval of odd numbers for some r, from r up to r times k to the 1 minus epsilon. So this, based on r, this interval could be really small, in which case there aren't that many numbers. R could be really big, in which case the numbers are big, but there are lots of them. So we get this pattern again, that if we take the sum over the chromatic number, sorry, we take the sum, harmonic sum over the odd cycle lengths, then you can work it out, and it's at least half minus little of k of the 1. It should be a log k. My apologies. Okay, so we get that it goes to infinity, and it goes to infinity with 1/2 log k, which is tied up to the 1/2 minus little of k. This is a smaller interval than in the even cycle case, I should note. But we can still prove that lots of sequences are unavoidable with high chromatic number. So for example, exponentially bounded sequences of odd numbers are unavoidable with high chromatic number. Okay. So we constructed odd cycles, even cycles, and then we can use them to construct odd cycles as well. I'm just going to recap the kind of implications before I talk about the actual constructions of even and then odd cycles. So this is a summary of what we had before. So for even cycles, we have this conjecture of Erdős, this question of Erdős, which is true, which we can also, I think, so we can also prove that if the average degree of graph is sufficiently large, then it contains a power of 2. We have correctly here that the harmonic sum of the odd cycle lengths goes to infinity, like 1/2 log of the chromatic number. And then we can also show that if the chromatic number of a graph is sufficiently high, then it must contain a cycle whose length is a prime number. So I've kind of sped through a lot of that, but I hope it's clear. What we're trying to do is find lots of different even cycles and lots of different odd cycles. And we construct these intervals. And these are some implications of this. These are kind of the main interesting implications, I think. So I will try in what remains to tell you as much as I can about the proof. And try to make as much sense as I can. So we use a very constructive approach to this. What we're trying to do is connect pairs of vertices, or what our methods are is to connect pairs of vertices with short paths to create a structure which can adjust the length of cycles. And I'll show you what the structure is shortly. And it's really quite a simple structure. A key feature of this is that we need to work in very sparse graphs. So I said that the Sudikoff or straight things don't work so well in very sparse graphs. So that's really the difficult case that we're trying to do. And in order to create these, carry out the construction, We'll use a form of expansion introduced by Komlosh and Samrady in 1984, to find subdivisions in sparse graphs. So it's a similar sort of question they were studying. If a graph has constant average degree, can you force the existence of some subdivision? So quick note, I can assume that the graph I'm working in is bipartite and has a minimum degree condition just by standard methods, by taking a bipartite subgraph containing most of its edges. So that will help. It'd be nice to know whenever I find cycles that they're even, for example. And I'll just give an outline of what I'll try to cover in the rest of the talk. So I'll start off by giving a rough, very sort of simplified version of the construction of even cycles that we use. Then I'll say a bit more about this expansion of Komlosh and Samrady. I'll be able to give actually some decent details on how you then can find odd cycle lengths. And then I'll try to cover some of the details that I skipped out over in one, and kind of point out the things I think are most interesting in how we carry out this construction. So we're going to construct even cycles in a simplified setting. And instead of constructing cycles, what I want to be able to do is, given any two vertices in a graph, I want to be able to find a path with a specific length between them. So if you could do that, we'd be very happy, because I can just take an edge and apply that, and I'll get cycles with a specified length. And by specific length, I'm being a little vague because we know I can't guarantee necessarily one fixed length, but maybe it will be a fixed length, a specific length, depending on the size of G. Okay. So this is our aim. This is the difficulty, to find a path with a specific length. And that's a difficult problem. So what's an easier thing to do is to find in the graph, or perhaps in a subgraph of the graph, a path which is just reasonably short between any two vertices, x and y. So let's say that we could do that, and that we can also do that vertex disjointly between lots of vertex pairs. And let's see if we can make some headway on finding paths with a specific length. So what can we do? Let's just to give you maybe an idea of what's going on. Let's say G has m vertices, and this thing that we can do, we can connect the paths with length at most m. So m is something that's logarithmic in m. So this is like the diameter of a graph. So I can find a path of length at most m between these two vertices. I can find two paths with length at most m, which are vertex disjoint between these two vertices. So definitely I can find a cycle with length at most 2m by applying this to some vertices. So if I take a cycle, let's take two vertices on it which are almost opposite. And let's attach them to x and attach them to y with paths with length at most m. And now what have we done? We have two paths in this subgraph. One, let's say, for some L. We have two paths which have length L and length L plus 2. So I find a really short interval of, there'll be even numbers or odd numbers depending where x and y lie in the bipartite graph. But if I want to find a path with length L, I go across here, loop down and cross to y. And if I want one that is two vertices longer, I go above instead. So because G is bipartite, I know this is an even cycle, so I know I can vary it by 2. Although I'd be even happier if I could vary it by 1, so that's not an important point. Okay, so you can find a very small interval, you can vary the path by 2. Okay, we want to do better, so you can maybe guess where we're going. So here's just a recap of what I'm allowing myself to do. Between lots of vertex pairs, we'll find a path with length at most m. Instead of finding one cycle, I can find lots of cycles. So let's say we're trying to find a specific path length, which is L or L plus 1, just depending on the parity of X and Y, whether they're in the same side of a bipartition or on opposite sides. Okay. I could vary the path by 2, but let's vary it by a bit more. So let's find some more cycles, each of them with length at most 2m, and let's connect them in a path from X. So I have a path coming from X through these cycles, and I have m cycles. These paths have length at most 3m each, so we're still linear in m. We're still much smaller than L, so let's lengthen the path until it's almost L. So by lengthening the path's shortest length, I mean we can take the shortest path through all of these cycles, and then I can lengthen this path in steps. So I can do this just by taking any other vertex and then applying my dream capability up here. I want to be able to find lots of vertex disjoint paths with a length at most m. So I can add on a path with length at most m. And I can just keep doing this and add on more and more paths of length m until I've almost got length L. So I'll stop between L minus 2m and L minus m. Then I can apply my ability again. I can connect through to X, through to Y. So I've now got a path whose length is in L minus 2m and L. And now all I need to do is lengthen it in steps of 2 until it has length L or length L plus 2, like so. And perhaps now I have the length I want. So this is, I think, a really straightforward idea. This is the kind of day one idea we had whenever we were discussing this. So all the difficulty is kind of carrying out this in some way, given this really weak expansion condition in very sparse graphs. You might be wondering, so I can connect different vertices around the cycle, so I could vary it by more than 2, but it wouldn't actually really help us get a much better result. So for simplicity, I've just varied it by 2 here. Okay. So this is the kind of our aim to carry out in even cycles. And this works if you can connect vertex disjointly lots of pairs of vertices. So to be able to gain some ability like this, although it's much weaker, we'll turn to the graph expansion that Comnosh and Semeradi introduced in 1984, as I said. So one probably rather simple corollary really of what they did was to show every graph G contains some subgraph H in which every pair of vertices is connected by a path with length, which is the most polylogarithmic in the size of H. So I probably haven't emphasized this enough, but all we know about the graph G is its average degree, so it could be a disjoint union of a whole bunch of different graphs. So what this does is just, it says kind of we can focus on some nice part of the graph in which will work. So in particular, they deduce this from an expansion condition. So this is the expansion condition we will use for our constructions. So a graph H is said to be an epsilon k expander if for each vertex subset, which is not too small, and its size at most half of the vertices in the graph, then its exterior neighborhood is at least this expansion function here times the size of U. And one thing just to note is that this is a function that gets smaller as U gets bigger, which makes it quite difficult to work with, as I'll cover. But on the other hand, it's about as strong as you can take expansion and be guaranteed to find a nice expander in any graph based on its average degree. In particular, combination sum really showed that for some small epsilon, every graph G with average degree at least 8D has a bipartite expander subgraph with minimum degree at least D. And this is expansion condition we're going to work with, although I won't do any calculations with it. So you've probably seen lots of this, or you probably can see immediately why it's useful for connecting pairs of vertices. So certainly, if I'm an expander and have minimum degree condition, then I can connect any pair of vertices by a path with length that's polylogarithmic in n. So if this expansion was a fixed constant epsilon, of course, then this would be just log n here, but because of this log squared, we have a log cubed. Okay. But yeah, so if I take two vertices x, they have some minimum degree conditions, they have some neighbors, that makes me big enough for the expansion condition to kick in, and then I can expand and expand until these wizard hats intersect, and I find some path between x and y. So the problem here is that it's just one pair of vertices that I've connected, and I wanted to be able to connect lots of pairs of vertices vertex disjointly, and that's really a challenge. And at this point, I'll just skip through the details, and I'll try to say a little bit about it in a while. And just state the main result that we get from this. So it's less complicated than it looks because of these curly brackets. What it's saying is that in any graph with average degree at least D, I can find a connected bipartite subgraph H so that I can find lots of paths in this interval here from L of H to L of H times D. Obviously, if I'm bipartite graph, I need, if they're in the same side, x and y, R needs to be even. If they're on opposite sides, R should be odd, which is surprisingly hard to write down, so it's easy to read. Okay, so this is no mention of expansion because it's all used in this dots. So we apply this common similarity theorem to find an expander. We carry out the construction I gave you, and then we can find this interval. So the reason I've written like this is the form that's useful for finding odd cycles in the graph. So I might talk a little bit about that. So how can we find odd cycle lengths, given that we've been entirely working in bipartite graphs and finding cycle graph paths there? Well, let's again suppose that we could find some nice structure. So this is the property of a graph that I like that we had before. So between vertices in the same side or in different sides, depending whether the length is even or odd, I can find paths between them covering every even or odd vertex in this interval here. And this interval is increasing with D, which is important. So let's suppose we could find within a graph not just one graph H that has this property, but we could find bipartite graphs H1 up to H5, which are all edge disjoint. In fact, they form a cycle, like I've drawn here, so that they only intersect on these vertices as drawn. So these 5 vertices here. And suppose they have this property we have. So you will note that if I take any cycle that starts at a vertex, lies entirely within H1 for a while, and passes entirely within H2, then H3, then H4, then H5, you can do the simple calculation and you'll always get an odd cycle. So if I use this box property up here, and for each of these graphs, take some path between the two connecting vertices of varying length, so of any length in their corresponding interval, then I'll get an odd cycle. And by varying each of those path lengths, then I'll be able to get many odd cycles. So this is a fantasy in that it won't always appear. But we can find something that's, I mean, once you have this idea, it's very straightforward to get to what you actually want. It's just a bit difficult to write down. So if we take now, this is me recalling the previous theorem. So this box property we can always find in a graph with sufficiently large average degree. You can always find a connected bipartite subgraph with this property. So now we want to work in a graph which has a high chromatic number, not average degree. So let's suppose we have chromatic number at least 3D. And let's iteratively try to find these graphs HI that I had on the previous line. So we'll just find as many of them as possible. So they're edge disjoint connected bipartite graphs, and they have this property. At some point, we won't be able to take any more out, and what will happen then? Well, the leftover edges, they can't have chromatic number at least D, otherwise it would have minimum degree at least D, and then we could apply this result and find another bipartite subgraph EH. So what's left behind has chromatic number at most D. So in fact, therefore, what we've removed must have chromatic number at least 3, and therefore it must contain an odd cycle. So this odd cycle is very similar to this cycle around here. It just might be a lot more complicated. It might switch between different graphs HI. The graphs HI that are in might overlap in vertices. The same one might appear more than once. But you kind of have a feeling that if this happens too much, then you can find maybe a shorter odd cycle or a better odd cycle. So roughly speaking, if you take a minimal such cycle in a certain way, you don't necessarily want to replace all of the edges using the box property, but maybe if you replace every second edge or some subset of the edges so that you're making sure all the paths you use are vertex disjoint, then you can do this and create many odd cycles. So that in our paper is not really that difficult. It's, again, whenever you write these things down, they look a little messy, but I think it's all very straightforward. The real difficulty is just being able to find these even cycles and carry out this construction. So I'll try to say what I can about this. So as I said, I was fantasizing that we could create lots of vertex disjoint paths between arbitrary vertex pairs in an expander. And we can't really do that. If we have minimum degree at least D, then we can only reliably connect about D arbitrary vertex pairs. And the construction I talked about certainly had at least M, which was about log cubed N vertex pairs to connect. So again, I'm thinking about D being a constant and N being much, much larger. Okay, so connecting vertex pairs is hard. We could never find that many connections. So what you can do instead is you can connect larger vertex sets. So again, for each epsilon and delta, if we have this expander with m vertices and minimum degree condition, we can connect vertex pairs x and y, pairs of vertex sets x and y, with a path with length which is polylogarithmic in n. That's what I could do before with single vertices. Here it's better because I can actually do this having removed any vertex set W, as long as W is not too big compared to, as long as W is small compared to X and Y, should we say. So it's maybe W is at most 1 over log cubed n times the size of these sets. And the general thing as we make these constructions, we want to find a bit of it, like one of these cycles, something like that, and then we'll add them into the set W and we'll avoid it going forward. So that's okay, but this set W is going to get reasonably big in size, so it's going to get polylogarithmic in size. So the connection of vertices, I can't do that. So every time I find something, I want to find it in a certain way so that it's easier to make the connections that I want. So for example, a key part of it is instead of just finding cycles here with X and Y, we find something we call adjusters. So an adjuster is simply a cycle here, and then I've drawn a triangle onto both sides. So this triangle X represents some larger set of vertices and has the property that it's well connected to X, so it's like an expansion of X in those neighborhoods. And the same thing for capital Y and little y. And certainly if X here is big compared to the cycle C, then I can expand it and use it to make connections to other adjusters. And then whenever I just consider the paths I find, I'll have the structure I was drawing earlier, so just the cycles with paths between them. So in particular, if we're able to find these adjusters so that the ends X and Y are really big and much bigger than W, the set of what we've constructed so far, then that will be very helpful. And in an expander, it's not very difficult to construct one of these. So how you can do this is start off by taking a minimal cycle and picking the vertices X and Y that are almost opposite. And then just look at the neighborhoods of X. And as I expand out, I won't encounter the cycle C very much, otherwise I'd have a smaller cycle. So that really limits the speed at which I encounter the vertices in V as I look at the neighborhoods going out. And between that and the expansion condition, that means that I can expand this set arbitrarily large. So I can make it as large as I want. The only real restriction is I'm going to add it into the set W, so it shouldn't be too large. So it will always be polylogarithmic in N. It's a little bit more difficult to then expand from Y because I want to avoid X, but let's not go into it. It's really not too hard to work out. So I can find one adjuster like this in an expander. Relatively straightforward and clear. The real challenge is to be able to do this having already constructed things and set them aside. So given this set W, can I find an adjuster within the remaining vertices that I've thrown out? And at this point, it's maybe there's a lot of information, so a bit hard to follow, but this is kind of the flavor of how this sort of thing looks. So we've removed some vertices W, and we want to find something else. So we better have some edges left. So if it turns out that if there aren't many edges left, then the edges from the rest of the graph to W, there must be lots of them from the minimum degree condition, and that gives me a subdivision. And just the important point there is that within this subdivision, everything is really well connected with lots of different length cycles. So we'd be really happy if we could find one of those. So we can assume that doesn't happen. So there are lots of vertices left. Sorry, there are lots of edges left when I remove W. And therefore, as I mentioned before, we can take an expander within them. I've marked in red this and a later point is kind of the most interesting novel aspects I haven't so much seen before in these sort of constructions. So we take a further expander and therefore just like above, we can find an adjuster in it. Except I've called it a proto-adjuster because the problem is anytime I say I'll jump down to an expander, the size of the graph might jump down hugely. It might become constant in size. So that's a big issue. So I can find something like this adjuster, but the ends of X and Y are really small, and they don't really work with what I found before. So I want to make them bigger so I can try to expand them. If that goes well, then I'll be really happy. So let's say it doesn't happen. And if it doesn't happen, then I've found some bad set which doesn't expand in the graph H minus W. Okay, but I don't give up that easily. I just set it aside, go somewhere else in my graph and try to repeat this. Find another expander, find another proto-adjuster. And if I keep failing at this, then what I get is I get many disjoint bad sets. That means I have many sets which don't expand in H minus W. That doesn't contradict my original expansion because they're all much smaller than W. But if I put them together, then I'll get a big bad set which is much bigger than W, which doesn't expand that well in H minus W. So I keep trying to find an adjuster. Every time I fail, I find a set which doesn't expand. They all might be small, but I put them together. Maybe that gives me a contradiction. So the issue with this here, and like really the key point that we really try to emphasize in our paper, is how to get around this. Get around the problem that this doesn't actually work because we have a sublinear expansion from convolution to semiriding. So individually, each of these sets might not expand, but we have this expansion coefficient which decreases, slowly decreases, but it decreases nonetheless as the set U gets big. So that, I don't think I can call it a naive approach because it's probably deep enough in it, but that approach doesn't work. So this is sort of the key point that let us get all this stuff to work. That's exactly what I told you. So this big bad set may still expand because it's not required to expand very much. So the strategy is kind of quite specific to the situation, but I think it's quite a useful, like a common enough situation if you were trying to construct things in expanders, which is why I wanted to cover it. So we set up our situation to make sure that the bad sets don't have a very large neighborhood in W. And we can do this by just making sure those bad sets all have some maximum degree condition out into the rest of the graph. So make sure the bad sets don't extend sharply into W, they don't have a big neighborhood. That lets us find, and then we find very, very many bad sets. So in particular, we can find many bad sets with the same size, which have the same neighborhood in W. So they have the same neighborhood in W, and it's not very large. And then we combine them together. And the key is to combine enough of the bad sets so that we're larger than their neighborhood in W, but not enough that we decrease this expansion condition by a great deal. And that allows us to find a contradiction. Okay, so I say this mostly in case you ever find yourself constructing things in expanders. This is something it took us a long time to realize, but was very useful. On my final slide here, I will finish with just a couple of open questions and a comment on the limitations of our methods here. So the expansion I discussed, we were finding paths which have length of around log cubed n in the worst case. So the construction I showed you, the shortest cycle in this expander with m vertices would have length around, well, the absolute best we could do is log cubed n. So the best possible interval we could have would be log cubed n to n. So therefore, we can't hope to do any to show that a sequence is unavoidable with any weaker condition than an entry is at most the exponential of the cube root of the previous term. So as this is written down in the paper without making it as best as possible, list 3 is at 10, but we definitely can't reduce the 10 to 3. And it seems very plausible that actually this third should be a 1. So yeah, this sequence that is really sharply increasing is probably still unavoidable. So I think that's a really interesting question. And then finally, we showed that every graph of minimum degree, at least some constant, has a cycle whose length is a power of 2. And we haven't worked out an explicit constant. It's probably large, but not unreasonably large. But this is a very interesting conjecture of Erdős and Hajnal that actually every graph of minimum degree at least 3 should be enough for cycle whose length is a power of 2. So that's everything I have. Thank you very much for listening.
Okay, thank you, Richard. And I would ask everyone to unmute themselves and give Richard a round of applause. So please, if you have any questions, then just unmute, or then just go ahead with your question while unmuted. So would your method allow to give a little bit more than cycles? I understand that cycles are by far the most interesting case, but could you have some theta graphs or something?
Oh, I'm not entirely sure. So we have written down, you can find subgraphs which are vertices connected by long paths of specific lengths. So the original problem we were looking at was the problem of Thomason from 1989, Carson Thomason. If I give you D by making the average degree be large, can you find a subdivision of the complete graph of D vertices in which each edge is subdivided the same number of times? So those sort of subgraphs where you have vertices connected by long paths, where you allow me to have very long paths, but I can tell you a lot about the lengths of them. This is the sort of thing you get.
Okay, yeah, thanks.
So Alexei asked the question in the chat whether we solved this conjecture of Thomason. Yes, we did. As we've written it down, you could make it more precise. Probably you only need average degree and constant times d squared to get this subdivision of kd. And we just wrote it down that there is some function depending on d. Yeah.
Okay. So that will be
Is the last conjecture known for higher average degree?
Yes. Which conjecture, sorry?
The Erdős and Hajnal one.
Yeah, so this is the one that we proved that was on the previous slide. So as long as your average degree is a high, large constant, then you have a cycle whose length is a power of 2. But we haven't calculated what average degree we would have. based on that. And definitely, so it's really the stuff that kind of kicks in, it's not too bad at all, but you need powers of logarithms to be smaller than n. So you want all these m's I was talking about, log cubed of n, you want them to be smaller than n, so you can do lots of things. So we definitely couldn't get anywhere near minimum degree at least 3, these methods.
So when do you expect to have this paper?
As soon as I finish proofreading it, so actually very soon. Yeah, I'd hope to get it out before this talk, but I'm running over.
Well, we could have waited 2 more minutes if it's the beginning.